Okay, so I'm going to make a review set of slides for the first exam for your class this semester. Um, all the questions that will be on the exam will come from these slides. If you're familiar with all the information on these slides, you shouldn't have any trouble with the exam. So what is geospatial technology? Who uses it? What is geospatial data? What does it have to do with geography? What's geolocation and Google Earth? These are all some of the things that have to do with geospatial data and GPS. So it's the technology itself is the use of several high-tech applications to acquire, analyze, manage, store, and visualize data. And when we do that, we're talking about geographic information systems, geographic positioning systems, remote sensing, any number of apps and websites. And who uses this sort of stuff? Well, government, forestry, law enforcement, public health, biologists, environmental scientists, humanities, consumers, big businesses, and even small businesses all utilize this technology in some form or another to increase their productivity, to better manage their advertising and sales, to figure out where things are or could be, to track epidemics, to determine potential locations for criminal activity, to manage natural resources, um, or any number of 1,000 other things. So here are some examples. You can see that you have at the top left, you've got you know county officials going around monitoring some sort of property owner issue. We've got agriculture using GPS to monitor yields. We've got researchers measuring some aspect of glaciers. We've got more farm activities. We've got sensors monitoring like earthquake stuff. We've got EMS people using spatial data to better come to grips with natural disasters. Here is an example of how you can use this technology to increase or improve your study of history. This looks at archaeology from Jamestown Island, and they look at tobacco pipe stems and how they changed over the years. They look at the different dig sites, and then at each of the sites they look at the type of pipe stems that they have recovered, and they place them in these pie charts. Bigger the chart, the more recoveries, and then within the chart, based on the colors, you can see the time period from when whatever was found, and so you can get an idea if there's a particular period of time that you're interested in terms of historical research, where from a dig site standpoint you might want to investigate. Um, you can also use it for a lot of environmental measures. Here's an example of looking at carbon monoxide concentrations using remote sensed data from satellites. You can use it to generate maps like this where you create some sort of a model for risk assessment for wildfires. And then you can identify, for example, in Virginia, which counties you live, and you can get some idea of how at risk that county is for wildfires. You can use it to plot crime data, criminal activity across a community, and not only show where the activities occur, but what type of activities it was. So that allows you to make sensible decisions about how to deploy resources in terms of what it is that you're sort of trying to stop or trying to prevent. You can use it to look at epidemiological information, such as outbreaks of the flu, to, for example, determine where you might want to focus federal aid in terms of providing like extra vaccines or something like that. You can use it to work off of websites to find the right neighborhood to build a house or to buy a home. In this example, we have a website Zillow where you can literally put in an address and see all of the houses for sale in that area. There's a new website called apartments.com where you can literally sketch your own polygon, the own neighborhood where you're interested in, and it'll identify all the apartments for rent within that area. So what is geospatial data? Well, it's data and information. It's understandable. It has some sort of location related with it, and attributes, and lots of sources, and it comes in lots of formats. What does all this have to do with geography? Well, it depends on if you ask a geographer. There's lots of ways of speaking the geographic language, and some people like to think of GIS as geography in action. But here are some examples. This is Las Vegas, Nevada, in a time sequence using remote sensed data with a false color image, and that allows us to see the developed area of Las Vegas and how it's changed from 1972 to 2000, and you can see the considerable amount of growth that has occurred in the area. You can also look at things like the map viewer here from USGS and use that as a means of acquiring other information. You can use OpenStreetMaps to find various roads and things like that. And then there's geolocation. Geolocation is this technique that allows you to determine where something is. And basically you can encode that information with, for example, pictures, tweets, any sort of thing like that. This looks at an illustration from the Charlie Hebdo incident some years ago, where the terrorists killed the French satirist for making a physical depiction of the Prophet Muhammad. And once they did this, there was this worldwide trend in some locations of posting the tweet, "I am Charlie too." And this is a heat map of those tweets, and you can see based on the number of retweets or tweets with that phrase, that hashtag, where in the world they were. So what is Google Earth? Google Earth is this free web-based sort of pseudo GIS. It works off of a virtual globe in 3D, allows you to zoom in. You can do some querying and some analysis, but it is somewhat limited. I think it probably technically meets the definition of a GIS, but it's not as powerful per se as something like QGIS, ArcGIS Online, ArcGIS Desktop, or Pro. So, when you think about GIS or geospatial information, one of the things that comes up is, where in the world are you? And it turns out it's not as easy a question to answer as you might think. To figure that out, you have to understand coordinate systems and how they work, and that involves a lot of things like datums and GCSs and 2D maps and other things. So let's talk about datums. Okay, we've covered this pretty extensively in class, and I'll go over it briefly again. A datum is the basis of a geographic coordinate system. The Earth, it's not really round. At best, it's roundish or vaguely roundish. So what we do is we take something called an ellipsoid, which is basically what happens if you take a sphere and mash it flat a little bit on the top and the bottom. It's still a perfect mathematical shape, but it's not round per se. And then we look at the geoid, which is this imperfect shape of the Earth, and it's based off measures of gravity of where we would assume mean sea level would be around the globe, and that varies based on the composition of the planet and how strong or weak gravity is at different places. Now, figuring out this shape is not an easy task. There's an entire scientific subfield called geodesy that goes about measuring the shape of the Earth. Now, we've said earlier that a datum is the basis of a geographic coordinate system. What a datum really is specifically, it's how we take a specific ellipsoid and fit it against a geoid that we have, or this measured, defined shape of the Earth. And once we do that, we call it a datum, like NAD 27, NAD 83, or WGS 84. And if you have to change between datums, you have to go through something called a transformation, which is just a means of changing from one datum to another. Here's a nice illustration of what we're talking about. You've got this surface of the Earth, and based on that surface you get some gravitational measures that gives you something called the geoid, which is that sort of mean sea level calculation. And then we have this ellipsoid, and then we move the center of that ellipsoid around to line it up as best we can for the geoid, sometimes for the entire planet, sometimes for just specific areas. And as you see in this example, some places the lines are under the geoid, some places they're over, and some places they're pretty much spot on. And that's just the way it is. Once we have a datum, we can then use and create a GCS. The GCS is the geographic coordinates. It's angular degrees. It's based on latitude and longitude, and it's based off of that ellipsoid that we use to create that datum. And so from the center we can identify the prime meridian and the equator and measure angular distances or in specific directions, east, west, north, south, to figure out specific locations on that perfect mathematical shape that is roundish. And those are typically be in degrees, minutes, and seconds, or decimal degrees. Time zones, if you have difficulty understanding how like UTMs work, time zones pretty much are a good way of thinking about it because it's a very similar concept. So here we've got a globe, and we've got degrees of longitude and latitude, and so this would be a GCS. And here are time zones, and the time zones loosely are very similar to what we would see in a UTM system, where we've divided the mapped out 2D version of the 3D globe into regions running north to south, broken apart east to west. The next thing we need to talk about is map projections. And so we had a few slides back a nice globe, and then we had a nice flat map. Well, turns out it's not just a trivial thing to go from one to the other. To go from a round globe to a flat 2D map, you have to do something called a map projection. That's a PCS, a projected coordinate system. It's when you take the roundish thing and make it flat. Projections distort things. The most common class of them that we come across are the Mercator projections. They've been around since 1569. They're primarily used for navigation, or at least that's what they were developed for. And the big issue is they distort size, but not distance or direction. And it turns out if you're sailing from one place to another, it doesn't really matter how big the place is you're sailing to as long as you can find it. So it works really well for that. It's a cylindrical projection, but there are other kinds of projections, azimuthal, conic. And then in modern sort of GIS, there's a couple of systems we use pretty commonly here in the US, and that would be UTM and the state plane coordinate systems. There are other systems as well. Within like the state plane, for example, there can be azimuthal, conic, and cylindrical types of projection. These are just different ways that you physically convert the 3D object into the 2D object, and these are the examples of that. The UTMs typically are the cylindrical, and a lot of times the state planes are conic. So here's a nice UTM projection, and it does a really good job of keeping distances and directions correct, but it does so at the expense of size, and that is why Greenland, which is this large sort of purpley brown chunk of land in the upper middle of the map, is roughly the same size as Africa, when in fact it is only 1/17 or so the size of Africa. UTMs are really cool. Divides the entire planet up into 60 zones. Each zone is 6 degrees wide. 6 times 60 means 360, and that means it covers the planet. And what happens is, for example, if you're looking at some place in, say, Virginia, you're either going to be in zone 17 or zone 18. And if you look left to right, going from the center of the screen, you get to zones 17 and 18. The numbers 17 and 18 go up, and you can see that Virginia sets in 17 and 18. And that would be zone 17 or zone 18 north, depending on which part of Virginia you're in. The thing about UTM zones is they're really, really good inside the zone, and then once you get outside the zone, they start to create some distortions that create problems. So I want to talk just for a bit about the concept of geocoding and how some of this stuff works and how some of these systems like UTMs work. So here we have this line here, that's the 13 north line, and we have this point location, and obviously it could have all kinds of different coordinates, but it's Mount Rushmore, and so the coordinates that we looked it up was 123,733.22 meters east of the zone's principal meridian. That means it's to the right of the zone 13 principal meridian, and it's a certain distance north of the equator. Now, we know that that line, that 13 north line, is a specific distance from the prime meridian, and so if we go back east, we take that number away from that, and from that we can work out the exact distance in terms of how far it is and how north it is, and it gives us our physical location on the 2D map for that. State plane system, like I said, it doesn't follow the UTMs. It divides the states up into sections, and the sections are defined by the states as they feel appropriate, and they follow something called FIPS areas. And the FIPS is a unique identifier that relates to existing infrastructure lines like counties and cities and that sort of stuff. And so these state plane zones they won't cross a FIPS line. So for example, if you look at Kansas, and there's a Kansas North and a Kansas South, if there was a county or something in Kansas that was across both of those zones, then the state plane zone wouldn't intersect the middle of a county. The county would be either in the north or in the south. That's why when you go across Kansas, you see the line looks straight for a while, and then it dips down, goes back up. That's because it's following these arbitrary man-made boundaries. And you can see a lot of states like North Carolina and Tennessee and Montana and Nebraska, they only have one state plane zone, and that's fine. Others have multiple ones. It's literally up to the states on a state-by-state basis. Now, what happens with all these different projections? Turns out they lead to slightly different shapes for things. And when we say about how accurate or not accurate they are, how much distortions they cause, when you look at a small enough area, the distortions are minuscule and they're not really even enough there to bother with. But the larger the area you look at, the more pronounced they become. And so here we have two maps of the continental U.S. One is in a Lambert conformal conic projection, and one is in a Mercator projection. Both of these are projected coordinate systems. One is cylindrical and one is conic. Conic projections tend to give everything that sort of curve pointing up towards the North Pole, where Mercator projections tend to flatten things out and stretch them. And you can see how they're at that point where we're looking at there in the middle of Kansas. They're almost identical, and right where that black dot is, it's probably identical. But as you move to the east and to the west, to the north and to the south, you can see that there becomes a significant change in the shape from one to the other. So when you go from one projection to another, it's no big deal if everything's in the same datum. You just work back from the projection to the GCS and then into the new projection. It's more of a problem if you have different datums. Then you have to do a transformation and do the shift. A bigger problem is when you don't have your spatial reference. In other words, when the information the software needs to be able to read the coordinate system doesn't exist, that's a problem. Identification of known locations on data with unknown locations, spatial reference and corresponding same location on the data with a known spatial reference. Wow, that's a lot of words. What we're talking about is this concept of georeferencing, and so it's easiest to think of it as aligning unreferenced data on one map to a reference data layer on another. So imagine this. You got one map that has the proper GIS related information to it, and then you have a picture. It's of the same place as the map, but it's just a picture. And what you would do is identify common locations or features in the unreferenced, unspatially developed image to the exact same location in the map that has a spatial reference. And after you go through and do this in several times in several places, this process of georeferencing sort of bends and aligns the image to the map and creates a new spatial data file that uh, will have all the corresponding spatial reference with it. Now, when you go to do that, there's a couple ways we can do it. Sometimes it's simple rotation, just twisting things around. Sometimes it's a skew. Sometimes it's a translation or just literally moving it some distance. Sometimes it's scaling, making things larger or smaller. Go through this process, identify these control points, these common locations, and the process then creates new locations with new coordinates. Then you compare the new coordinates to the known coordinates on the existing map. You see how far off they are, and you measure residual, and then you add those residuals up, and that's sort of how you get this idea of how good a job you did. And then once that's done, you have two options. You can sort of update the georeferencing, or you can rectify it. Now, what does that mean? Updating the georeferencing basically just creates a file that goes along with the image that tells the software all the information it needs to properly display the image. If you rectify it, it makes a brand new image. That means it has to create this grid spacing, resample it. It creates some distortion, some blurring, some smoothing, but it gives you a brand new, completely geo-referenced, integrated, spatially referenced data layer. And here's what we're talking about. Here's an old hand-drawn map of Exeter College in Britain, and behind that is a modern-day georeferenced aerial image of the same location. And this was georeferenced, and basically they looked for common locations that exist on both of the maps, such as roads and rivers and streams and certain buildings and intersections. And once they identified enough of those, it twisted and bent and tugged and pulled the image of the Exeter map from old until it lined up to those known points on the current image. Now, this is all well and good, but what if you don't actually have some of this information, or how do you know where things are when you're doing it? And it turns out that's where the second part of this process comes in. It's not just the information system, it's the global positioning system, which is made up of an array of satellites that rotate around the Earth, and from those you can identify where things are at and where you're at. And so a global navigation satellite system, a GNSS, is what we're talking about. And they're basically made up of these GPS satellites that are in orbit around the planet, and they transmit information back and forth to ground stations, and then GPS receivers pick up the same sort of signals from the satellites, and from that they can determine where they are, because the satellite is in a known location, and the GPS receiver, if it attaches to enough satellites, can then figure out where it's at as well. So the way that it does this is something called trilateralization, and we're going to look at that a little bit. If you get a signal, it'll give you a loose idea where you're at, but it's not real specific. And so there's some error into the calculation, and the fact that it's a distance measurement doesn't mean it hits a single point. It hits it like some area. In this example, we're saying that we know we're within about 50 miles of, say, Ann Arbor. We pick up a second satellite signal, and from that one we can know that we're, say, roughly 150 miles from Traverse City. And if you see these two radiuses intersect each other, there's only two spots that are exactly 150 miles from Traverse City and 50 miles from Ann Arbor, and that's Lansing and Flint. Now, this is looking at it in 2D. In a minute, we'll talk about what happens when we go to 3D. If we add a third satellite, say one that says we're 60 miles from Kalamazoo, that one intersects Lansing. With three satellites, trilateration, we now can identify in 2D where we're at spatially. But turns out if you do that in 3D, it identifies two possible locations. one on the surface and one up in the air. If you want an accurate measurement of your elevation, you really need a fourth satellite to get that fixed improved, because that will then eliminate one of those points conclusively and give you a better estimate of which one it is. So, what are some of the things that jack up our signal? Well, the signal comes from space, it goes through the ionosphere and the troposphere, and things happen. The signal propagation is altered by parts of the atmosphere, things that interfere with the electromagnetic signal, particles floating around, dust, dirt, water vapor, any number of things, um, magnetic fields, airplanes. Anything that can get in the way potentially does, and could, either for a brief moment or a lengthy amount of time, cause some variation in that signal. So when this happens, that time number that we get from the satellite will be off, and so it won't give us a super accurate location. There's other things that cause problems too. You would hope that your signal comes from the satellite on a single path to your receiver, but in reality, there's multi-path errors where the signal, for example, comes down, hits a shiny barn roof, and then bounces off to your tractor, just like the signal coming down from above, but it has a much longer delay because it traveled further, and so that complicates the signal, and your GPS doesn't know where it's at. So we do this using something called differential GPS, which allows us a means of correcting this, because we have these radio stations that transmit known information up to the satellites, and the satellites correspond and correlate with that, and the vessels or whatever it is it's trying to navigate can pick up a signal from the ground station, which has additional correction information and whatnot. It goes along with the satellites, and from that it can then get a better fix on your location. The most common system of this sort of nature is something called WAS, which is a Wide Area Augmentation System, and it runs off of a specialized ground station that feeds information to a satellite that transmits another signal. And this is based off of a bunch of reference stations, and it coordinates a whole lot of things to help improve it. And the net impact is, even in a cheap, like $100 handheld GPS unit, if you enable WAS, you can go from something that has, say, 10-meter accuracy down to something that has less than 3. So that's a pretty significant improvement.